get started today with our first speaker, Pedro Marcuello. Thank you so much, Pedro, for joining us.
Yeah, thank you. Just a second. Hi, thank you. So yeah, I'm gonna talk about. So I'm gonna repeat a bit the presentation that we did that morning on the all-in-one RISC-V that Semidynamics is presenting, and I'm gonna give some more details on the part of the vector and the tensor unit. So the way that usually the current SoCs are facing the IA applications is something like that. So we have the cores that they are running the part of the scalar part of the applications. Then the part that is more SIMD-like part of the AI applications, they are just outsourced to the GPUs, where they have all these SIMD functional units that they can run really fast and really well all this part of the code. But then the part of the matrix multiplications and the matrix stuff, they are moved to other block that is the NPUs, that they are really good on doing this kind of multiplication or convolutions. So if we take a quick look on what is a block that it's really common as the attention layer in the AI applications. This is common in Llama2 or any other AI applications. We can see that there are a bunch of matrix multiplications. So it means that the core has to send all the data to this NPU, big matrices there. They just do these multiplications there that they do really fast. And then we have this transpose that, hey, that part cannot be done in the NPU and needs to be moved to the GPU. So we have to make the CPUs to move our result from the NPU, move it to the GPU, do the result there, and then once that, we have to send it back to the NPU and do another matrix multiplication and do it again back to the GPU to do the softmax or any other function, and then back again to the NPU to do a final matrix multiplication. So this is very common, and we are doing a lot of moving of data from one block to the other and losing a lot of power and loss of time. So the thing is, on the current style is we have these three separate blocks. We have to move data from one place to the other. We end up with DMA intensive applications with high latency, with a very bad PPA because we have multiple caches at every block. And also, for the programmer's point of view, this is a nightmare because I have to learn three different software stacks. So I have to learn how to program CPUs, how to program GPUs, and finally how to program NPUs. On the other hand, what we are proposing in Semidynamics is, hey, let's try to have a single block that has everything. So we have a core, not huge, a proper out-of-order core. We have a vector unit that it can make the role of the SIMD unit, and we can make the role of the GPUs. And then we put a lot of matrix of elements, of multiplier elements, that they could be the tensor unit. In a way that, hey, with a single block, we are able to run the whole application without moving data. So we end up with a DMA-free programming. We have zero latency because the data is shared in a single part. So they are the vector unit, the tensor unit, they are gonna share the register file, and they are sharing the architectural state of the whole thing. The latency of movement data now becomes zero because they are sharing the same space, and especially it will be a single software stack. So for the programmers it will be great because yes, learning RISC-V, it will be okay to do all this programming. So that's the thing that we are somehow try to convey in this talk. So starting from the leftmost corner on the downside, we have a core that is part of that it's a four-way out of order. We can add a lot of other extensions that are required. On top of that, we have a vector unit fully compatible with, fully compliant with the RISC-V 1.0 spec. We go up to 2,000 bits on the data length, with 4,000 bits on the vector length, and out of order. And we are able to deal with all the data types. On the other hand, we also add a tensor unit that's gonna share the register file with the vector unit, and it can reach up to 8 tops, and actually just running with the small data types that are the ones that are really used in the AI applications. And finally, the thing that it's gluing everything here is the Gazillion misses. That is, to fit up this kind of beast that they are able to execute 8 tops or 16 gigaflops per second, we need something that gives some bandwidth and some memory. And this is the the thing that the Gazillion missing is doing. And the thing that we are proposing is just have a single new instruction for the tensor unit, that it's vector matrix multiplication, and it says, let's compute C as A times B plus C, and that's all, and we put the matrix A in some register, matrix B in some other register, and the result in some other registers. And then 2 new instructions just for loading the matrices and for storing. The BLRSE, that it's I give you the base address, I give you some encoding that says how many bit elements I need for per row and which is the total size of the row, and also for the store. So I think this is more clear here in the next slide, that it's this is how the matrix multiplication scheme, the program will end up in RISC-V, that it's just an 8 instruction loop. So the blue part, the 3 first instruction, it's how I load matrix A into my vector register file. So I just set the bit type. I said that the element is 16 bits, my LMUL is 2, and then I do the BLRSE of B8, so it means that I will load B8 and B9 because I said LMUL 2, and then I said in T1 I encode that it's I'm gonna have 16 elements, and I'm gonna have the row of and the size of the row. I'm gonna put 16 on the low side and the size on the high part. Then the green part, it does exactly the same, but loading the B matrix. In that case, since I'm going to use register from B0 to B7, I put LMUL 8, and I encode 64 elements, and I put the size of the matrix B on that side. And then once I do that, I just put vector floating point matrix multiplication. And that's all, and I'm going to iterate. And then finally, I have to store this data. And I just said, in that case, I keep the LMUL 8, and I said, okay, now I had to store 16 registers, I had to do it in 2 instructions, B16, B24, and I encode the size of the number of elements that I have in that matrix, that in that case is 64, plus the size of the register. But the important thing here is all about bandwidth. The computation and doing all the FMA computation inside the tensor unit is relatively fast, so it takes few dozens of cycles. The problem is that for the next iteration of the loop, it means that in order to have the tensor unit really busy, before executing that, while I'm executing that instruction, I have to do the loads for the previous 2. In that case, I have to store 10 registers from B0 to B9. 10 registers, in that case, we have assumed 2000 bits as a vector length, so it means that we have to go to fetch around 40 catch lines to the BPU. So it means that if your matrix multiplication, it takes around 40-50 cycles, it means that you have to provide a cache line every single cycle. So it's something that it's really, the thing that is really important in the tensor blocks are the bandwidth. So, and here is where Gazillion misses plays the role. So Gazillion misses allows you to have multiple outstanding misses in flight, and in that case, it means that whenever you are going to execute the next matrix multiplication, you are going to have the data there, and you are not going to stall the tensor unit. These are some numbers that we got on the yellow V3 performance. So we ran the different stages of the different convolution layers and so on. We got an average of utilization on the tensor unit around 80%, 75 to 80%, and we are having a number of frames per second around 33.03, with just a small tensor unit that is able to get 1 top per cycle. So we are with just a single block with a core vector unit and tensor unit, we are getting real-time performance. So just as a summary, because this is a short talk of about 10 minutes, so the thing is, we are saying that the AI is now, it's the new paradigm. Everyone wants to run AI, but the way that we are running it in multiple blocks separated. No, let's try to have it all together in a common block. We have the core, the vector unit, and the tensor unit. And let's try to have it in a single software stack that somehow eases the way to the programmers, and is what we are defending here, the all-in-one RISC-V. So that's all my talk. Yeah, please.
Thanks. Hello. Gazillion miss is a kind of transfer predictor? Or?
No, it's a way of having multiple. So the current course is around 16 to 20, 25 outstanding misses is the way that they are doing. We are able to have up to 128. So you need a special logic because the usual way to do it is CAM matching and so on. You cannot afford 428, so that's the special, our secret sauce. So we are able to manage up to 128 cache lines random and having secondary misses and so on. So that's the thing that we are doing. Any other? Okay, thanks a lot.